So we were doing the chemical bonding chapter, and we had completed at the point where we were doing the overall polarity of the molecules. So we said that to determine the overall polarity, we are supposed to check two things: the shape of the molecule and the polarity of the molecule. So shape, as we have already covered in the topic of Vesper theory, where all of the bond angles were determined using the repulsions between the lone pairs and the bonding pair of electrons. So these are the shapes which you have already covered: the octahedral, pyramidal, nonlinear. One such thing to be considered here is that all of these bond angles or shapes, the trigonal, planar, linear, trigonal, bipyramidal, octahedral, and tetrahedral, these are all considered to be the standard shapes. These are standard shapes in which no lone pair is present. So all those molecules which would have such type of the shapes will definitely give us the idea whether the molecule will be overall polar or non-polar. So about the polarity of the molecule, we were doing the example of the carbon dioxide, and we said that carbon has electronegativity value less than oxygen. The carbon value is 2.5 and the oxygen value is 3.0. There's a difference of 0.5. A difference of 0.5 is sufficient to create dipole, sigma positive and sigma negative. So carbon would have sigma positive and oxygen has sigma negative sign on it. Now the arrow over here is representing the direction from the less electronegative atom towards more electronegative atom, or in other words, it is directed from sigma positive side to the sigma negative side. Now that we have such a molecule in which the arrows are directed from carbon to either side because of two oxygen atoms, so we would have these two opposite sides of arrows. Now molecule, the polarity of the molecule will be determined not only because the bond is polar, but also because the shape is linear. That means one arrow is moving one side and the other is moving on the opposite side. To calculate the overall direction of the arrow, you should consider the resultant vector. If you remember the topic of vector addition of physics, have you studied this topic, vector addition, to find the resultant vector?
Yes, sir.
And Sharmeen, what about you?
Yes.
So the rule says you have to, if you have two arrows, arrow 1 and arrow 2, so the rule is head to tail rule. Head to tail rule, which means you start from the tail of first arrow, you put the other arrow on the head of the first arrow, and you start from head of first to the from the tail of first to the head of the last one. So applying this rule, this will give you simple zero value, because you start from 1 and you end at the same point, which means that by vector addition, the value is 0. That gives a 0 dipole. So dipole will be 0 for this case because of the linear shape. So that is why the CO2 molecule is 0. The CO2 molecule is non-polar, because there is no overall polarity in CO2 molecule. Now, if I take an example of water, H2O, so the shape of H2O is like this. We have the more electronegative atom as oxygen, whose value is 3.0. A slight mistake here. The value is 3.5. It's not 3.0, it's 3.5. 3.5, and the hydrogen value is 2.1. So the direction of the dipole would be from less electronegative atom towards the more electronegative atom. So hydrogen to oxygen, this dipole direction, and then again like this. Now we have to determine the overall polarity. So the overall polarity for this case will be net dipole. There will be a dipole in this molecule because we have to also include the lone pairs right now. This topic will be later on discussed after this, because we do have some lone pairs as well. But in the case of the carbon dioxide, the central element was carbon, and in this case, the central element is oxygen. So these two have differences in the terms of the presence of lone pairs. Our next example is HCN. Now HCN has three different elements. Hydrogen has value 2.1, carbon has 2.5, and nitrogen's value is 3.0. The value of 3.0 belongs to nitrogen. Now you can see that the difference is from 2.1 to 2.5, and then from 2.5 to 3.0, which means there is a clear direction of the dipole from the least electronegative atom towards the most electronegative atom. Although the molecule is a linear shape, but the direction of arrows are not reversed or opposite. Instead, they are in the same direction. So because of this reason, the molecule will be considered to be polar. So molecule is polar here. Is that clear to both of you?
Yes.
Yes, sir.
All right. So if by chance there was some sort of reverse arrow, we could say that some of the dipole is cancelled. But one thing more, if I have let's suppose oxygen atom, what do you two think? Should that molecule would be polar or non-polar if there was oxygen instead of hydrogen? Would this molecule would be polar or non-polar? And why? Yes, please. No answer from any both of you. Okay, don't give me the reason. Just tell me, would it be polar or non-polar? I'm not asking the reason.
Non-polar?
Okay, and what about you, Fatma?
Non-polar.
Both of you are wrong. It would be a polar molecule. Now, why is that so? The reason is that although you can see the arrows direction are opposite, yes, these are opposite, but thing is that the difference of the values are not same. They are different. You have a difference of 1.0 here and the difference of 0.5 here. So basically the magnitude of dipoles are not similar. They would be cancellation to some extent, but not completely cancelled out. So you would definitely have an arrow in the left direction because the difference is greater here. There's a difference of 1.0. So because of this reason, this molecule will be considered polar. So this is how we need to check. We need to check the polarity of the bond, and we need to check the shape of the molecule. So that's why this molecule would be a polar molecule. Is that clear?
Yes, sir.
All right. Now, let's take some more examples. We have an example of CHCl3 molecule. No, before that, I will go towards CCl4. Carbon tetrachloride, CCl4. Now this is the shape of carbon tetrachloride, CCl4. Here we have a dipole difference of carbon and chlorine. Again, I will put the values 2.5 for carbon and we have 3.0 for chlorine. Remember that nitrogen and chlorine both have similar value of 3.0. Now, all of the carbon to chlorine bonds are polar. So we have all the bonds polar. But the thing is that this molecule is a perfect tetrahedral shape. This is a tetrahedral shape here. So the vectors will canceling out each other. How would they do it? Now you should remember the tetrahedral shape. How does it look like? You have two atoms in these directions from this central one, and two atoms would be in this direction. So if you try to compute the resultant vector, in this case, it will be giving 0 value. So the tetrahedral is a standard shape, and that's why all the dipoles or all the vectors will be cancelled. You would definitely you have to say the word dipole in your answer. For reference, I'm saying vector, but do not use the word vector in your answer. So all the dipoles or all the dipole moments will be cancelled because of this reason. Is it clear to you, both of you? Are you getting the point?
Yes.
Yes.
So, all right. So that's why this molecule is a non-polar molecule. Now take the other example, CH3Cl molecule. Now in CH3Cl, we have 3 hydrogen atoms and 1 chlorine bonded with the central carbon. Now the difference of hydrogen to carbon there is a difference here, and also there's a difference with chlorine to carbon. So all the bonds are polar. All of them are polar, but the problem or the difference here is that the dipoles of these three will not be able to cancel the dipole of the carbon to chlorine in terms of the vector addition. So they will be overall direction of dipole starting from the least electronegative atom towards the most electronegative atom. Hydrogen has a least value 2.1, carbon has 2.5, and chlorine has 3.0. So there will be a overall direction. There will be an overall direction in this molecule. So because of this reason, the molecule is polar. So these were the example, and one more example is about the CHCl3. This is CH3Cl, and this is CHCl3. So similar concept will be applied here. Carbon is bonded with 3 chlorine, so they have their dipoles. And also carbon to hydrogen has also a dipole. Now, again, in this case, the dipoles are not of equal values. They are of different, and because of this reason, there will be an overall dipole. So the direction, where should be the direction of this dipole? From which side to which side? Yes, students?
One will go from hydrogen to carbon, and then it'll go from carbon to.
Yes, very good. So the direction will be from hydrogen to carbon, then from carbon to chlorine. So yes. Now, is it clear to you, Shamin?
Yes.
lone pairs and dipoles. Now, the other type of the molecules are those which contains the lone pairs. So lone pairs are also present in some of the molecules. Example are ammonia and water. Now, if you remember that lone pair is such a such a pair of electrons which has more electronic density in the space as compared to the bonding pair. The bonding pair, let's suppose between nitrogen and hydrogen, this electronic pair is being pulled or attracted towards both nitrogen and hydrogen atom, and that's why the electron density are not spread out in the space as much or as compared to nitrogen. The nitrogen's lone pair on it is not being pulled by any other atom other than nitrogen, so that's why its electronic cloud is more in the space. So this high electron density of the lone pair will create a good electron density in that site. So that's why there will always be a polarity, overall polarity of the molecule in these type of the molecules. It will be directed from the least electronegative atom towards the electronic pair, so lone pair. So that's why there is a polarity from hydrogen to nitrogen and then towards the lone pair. This arrow is ending at lone pair. Similarly, for the water, we have two lone pairs on the oxygen atom, and they are even greater. There is a greater electron density in this molecule as compared to ammonia. So that's why the overall polarity is directed from the hydrogen towards the lone pair. So all the molecules but be mindful, one more thing. We are concentrating on, or we are uh, taking into account only the central atom. We are only considering the central atom, not the other atom which are side bonded to the central atom. Let's suppose if I say we have the molecule of nitrogen bonded to chlorine atoms instead of hydrogen. So nitrogen has only one lone pair, whereas chlorine have 3 lone pairs. So we do not consider these chlorine atoms, we have to consider the central atom, whether it has a lone pair or not. Since it has a lone pair, so there will be a polarity, but we do not consider the lone pairs of the other atoms other than the central atom. We have to be concerned with the central atom. Okay, now the next topic is of the explanation of the intermolecular forces. We had introduced the topic of intermolecular forces, but now we study all those types in detail about the intermolecular forces. So I'll be using this word most often, IMF, instead of van der Waals forces, because as I told before, van der Waals force was a name given to two things. It could be given to the intermolecular forces, it could also be given to the instantaneous dipole, induced dipole forces, although intermolecular forces is the major group and its subclass is instantaneous. So in my opinion, it is not a good word to describe both things at the same time. Anyways, intermolecular forces has 3 types. One is the identity forces, the other one is the dipole forces, and third one is the hydrogen bonding. So first one, identity forces. Now, identity forces are such type of the forces which are present every time in all the types of the molecules. These are present every time, and they are present in all molecules. I'm using the word molecules, so be mindful about the word molecules. So these are present every time. Now, how are they present and how are they created? That's the thing. Do you two can you two must have studied this topic before. Sharmi, you have also covered the AS, right, before?
Yes.
So, can any of you tell me the story behind the creation of the ideative forces? I just wanna see if you know.
The electrons are constantly they create an instantaneous
Your voice is disrupting between. Please repeat. Fatma, please repeat. Yes, Fatma. And Shirmi, what about you? Do you know any basic basis behind this?
I don't remember.
Okay. Fatma, you were telling, but your voice was breaking during that.
Sir, I said the electrons are constantly moving, so they create a dipole movement, which is how the instantaneous dipole is created.
Hmm. And how the induced dipoles are created? Very good. You are right about the instantaneous dipole. So let me tell. The electrons, as you know, within the atom or within the molecule, they are constantly moving. They are not static, they are dynamic. So, because of their dynamic movement, they are constantly moving around. So, there could be a chance or there could be a time or moment where the number of electrons on one side of the molecule would be greater as compared to the other side of the molecule. Let's take an example of a molecule A. This is a molecule A bond, which consists of two atoms. This is first atom. This is the second atom of the molecule A. Now, this is just a random picture which indicates that the electronic distribution is totally symmetrical on both the atom 1 and 2 of this molecule A. But there could be a time, any particular moment, when the electronic load on the atom 1 would not be symmetrical. There will be greater number of electrons in atom 1 and there will be less number of electrons in atom 2. So if the electrons are more saturated or they are crowded on one atom, that would mean it would have a sigma positive sign on it. So charge negative charge atom is to be considered this one. This would be more electronegative, or this should be having more electron density. And when it has more electron density, then definitely the other atom has less number of electrons. So the atom 2 would have less electrons. That means it will be considered as sigma positive. So this is how an instantaneous dipole is created in any sort of molecule, especially of those which are naturally nonpolar. We are more concerned with those molecules which are nonpolar, because nonpolar did not have such electronegative difference between the atoms to become a polar molecule, or the shape of the molecule is used to cancel out their dipoles. So we are more concerned with the nonpolar molecules. So this is an example of a nonpolar molecule, like for example Cl2, O2, H2, F2, etc. So these molecules are completely nonpolar. So this is how the instantaneous dipole is created in the molecule A, whose picture is depicted here. This is the one which reflects the presence of the instantaneous dipole in the molecule A. And the direction is from dipole arrow is represented here. Now we have got an instantaneous dipole. Sharmin, is this clear to you?
Yes.
Now that we got an instantaneous dipole, now this instantaneous dipole is definitely surrounded by the molecule B. The molecule B and molecule A are definitely of same type. They are, let's suppose if it is a Cl2 molecule, then it is also a Cl2 molecule. They are both same. So what happens during this? that the electron density of the atom 1 in molecule A, this is atom 1, this is atom 2. So the electron density of the atom 1 in molecule A will now try to repel the electrons present on the nearby atom 2 of the molecule B. So the electrons, they are now repelling each other. They are pushing each other. So what happens in the molecule B, that these electrons will shift on the other atom. They will move on to the other atom. So when they shift towards the atom 1, this will now create more electronic density on atom 1, and so similar sigma negative sign will now appear on the atom 1 of the molecule B. Sorry, this is molecule B. It's hidden over here. This is molecule B. So electronic cloud will be present more on the atom 1 and less electron will be there on atom 2. This is all because of the repulsion of electrons between the instantaneous dipole, which was already created before, and the molecule B. So this creation of the dipoles on the molecule B will now be called as the induced dipole. It's hidden in this text. It is the word induced. So I can write here, this molecule B will now become induced dipole because it has been created by the instantaneous dipole. Instantaneous dipole was created by itself, and that has created dipole in the other molecule, which will then become, or which will be called as induced dipole. So this is how instantaneous dipole and induced dipoles are formed, and then the forces between them are called IDID forces, or in instantaneous dipole induced dipole forces. Is that clear?
Yes, sir.
Yes.
Okay. So give me a second, please. So this is how the instantaneous and dipoles are, and both instantaneous and induced dipoles are created. Another thing is that the instantaneous dipole can also be termed as temporary dipole. So we can also use the word temporary dipole. So that's why we have the short form as TDID forces. So this was the whole story about temporary dipole or IDD forces. Now we have to consider some other factors which influence the strength of the IDD forces. Now in IDD forces, as we have just discussed, that these are the electrons which are forming the dipoles, which mean that जितने ज़्यादा electrons उस molecule में होंगे, they will be greater unsymmetrical distribution
Sir, आप screen
of,
sharing कर रहे हैं.
wait, I think I am sharing. किसको नजर नहीं आ रही?
It
Sir,
says
here
you
it's not
pause.
showing.
आप दोनों इकट्ठे बोली, क्या कह रही हैं आप?
Your screen isn't sharing for both of us.
शर्मीन, आपको भी नजर नहीं आ रही?
Yeah, नहीं नजर आ रही.
So unsymmetrical distribution of electrons होगी उतनी ही ज़्यादा जितने ज़्यादा उसके electrons ज़्यादा होंगे, तभी उसमें instantaneous dipole की formation हो रही थी. That means that those, if we compare two molecules, or you can say two different elements, let's suppose if I have a hydrogen molecule and I have a chlorine molecule. So definitely the size of the chlorine atom is bigger than the hydrogen, which means there will be greater number of electrons in Cl2 molecule as compared to the hydrogen molecule. And that will also create stronger IDD forces in the Cl2 molecule. So you can say they will be stronger or they will be greater IDD forces in the Cl2 molecule as compared to the hydrogen molecule. That is because of the greater number of electrons in that atom. So you can relate with the size of the atom, or you could relate with the number of electrons of an atom. In some cases, you will clearly see the size, and in some cases, you will clearly see the number of electrons. And the IDD forces are also very much prominent in the noble gases, neon, argon, krypton, because these are all considered as monatomic molecules. These are the molecules of only single atoms. And another thing which affect the IDD forces is the distance between the molecules, which means we have three different states: the solid, liquid, and gas. So definitely the molecules are closer together in the solid state. So IDD forces will be greater in the solid state of the same element, and they will be weaker in case of the gaseous state of the same element. We have one more example. The example of these hydrocarbons. Now, this hydrocarbon is in that particular structure where they are packed very closely. So close packing, let's suppose we have this molecule. Can you give me the name of this molecule? Just consider only one molecule here. Can you give me the name? What is the name of this molecule? Yes, students.
Is it butane?
Yes, butane. Very good. So this is one structure of the butane. And then we have the other structure of the butane, which is basically its isomer. And this is a branch structure of the butane. Basically, यही टॉपिक जो हम केमिकल बॉन्डिंग का पढ़ रहे हैं, these will be repeated in the organic chemistry in terms of the chemical bonds. So you have to link these topics with each other. The structure of butane in this way, which is the isomer form, isomeric form. So इसमें हमें जो नज़र आ रहा है, there is definitely less interaction between carbon to carbon. So if they are less compact, this is a less compact structure of the butane. So this less compact structure would lead to a less number of the IDD forces between the molecules. So there will be just one such closest distance for the IDD force to exist, and this structure would have more number of the points where the IDD forces could exist, like this. Like this. So that's how we have the difference between the strength of the IDD forces. Similarly, we have this pentane, and this is an unbranched structure, and this is the branched structure of the molecule. Now, what is the effect of the IDD forces on the boiling points? So basically, boiling points or melting point, these are the physical properties which rely on the strength of the intermolecular forces. They do not rely much on the on the intramolecular forces, because intramolecular forces has to do with the strength of the two atoms. But for boiling points and melting points, this is basically to decide how easily the forces between the molecules are broken. If it is an element A in the diatomic form, then these two molecules are bonded with each other through identity forces. You have to break this force to separate these particles from each other. So these will then be two different A2 molecules. But do not consider breaking covalent bond, because if you try to break covalent bond, it will not remain A2 molecule anymore. It will not be the molecule. It will be totally changed. So हमने देखना ये होता है कि how easily the bonds between the molecules are broken. That decides the bonding point. So if the identity forces are stronger, it would mean that it would require a higher temperature to boil that molecule or higher temperature to melt that molecule. So both the boiling point and melting points depend upon the strength of the identity forces. So if let's suppose we have an ethane molecule and the other one is pentane. So the ethene is a smaller molecule and pentane is a larger molecule, which means there will be greater identity forces in pentane as compared to ethane. That's why the boiling point of the pentane is greater than the boiling point of the ethane. So this is the difference between them. And it is also explained here that greater molecular surface contacts or stronger intermolecular forces, which means stronger identity forces. और आपको ये पता होना चाहिए कि these are hydrocarbons. So hydrocarbons have only the identity forces. They do not have the other type of the intermolecular forces. The other type of the intermolecular force is permanent dipole forces. Now, permanent dipole is those type of the molecules in which there are already a good difference of electronegativity between the two atoms. So A and B atoms जो होंगे जो different elements के belong करते हैं, उनमें जो difference होगा there should definitely be a difference of 0.5 till and equivalent to 1.9. अगर इतना difference होगा, ये कभी कभार 0.4 को भी consider कर लेते हैं. So if इतना difference हो तो उसमें clearly dipoles present होंगे. So there will be sigma positive and there will be sigma negative dipoles on them already, which means the dipoles are permanent. So it is basically a force between the dipoles of two different molecules. One such example is HCl. HCl में we have the sigma positive hydrogen and sigma negative chlorine. So इनका जो difference काफ़ी ज़्यादा है, 2.1 for hydrogen and 3.0 for chlorine. So difference is of 0.9. So that's why it's a dipole molecule. It's a polar molecule, so it will have dipole force with the other HCl molecule. And we also have an example of the propanol. अब ये आपको पता है ऑर्गेनिक केमिस्ट्री का मॉलिक्यूल है कीटोन. अब इसमें डायपोल कहाँ पर होगा? बिटवीन द कार्बन एंड ऑक्सीजन. सो यही आगे मजीद कीटोन मॉलिक्यूल्स के थ्रू इसी तरह डायपोल फोर्सेस से लिंक होगा. तो इसलिए द बॉइलिंग पॉइंट ऑफ कीटोन इज ग्रेटर देन द बॉइलिंग पॉइंट ऑफ द ब्यूटेन. अब इन दोनों को कंपेयर क्यों किया गया? बिकॉज देयर मैसेज आर सिमिलर, 58 ईच. इसलिए इन दोनों को आपस में कंपेयर किया जा रहा है. So again, the effect of the stronger dipole forces is on the physical state of the molecule. If the dipole forces are stronger, the molecule will tend to be more towards the solid state. And if you compare with the identity forces, then most of the molecules containing dipole forces should be in the liquid state, and the weaker identity forces molecules will be in the gaseous state. PDD forces are weaker as compared to ionic bonding, covalent bonding and metallic bonding, जिसका हमने पहले बात की थी कि ये इंटरमोलिकुलर फोर्सेस होते हैं, तो इससे तो वो वीक ही होते हैं. इंटरमोलिकुलर फोर्सेस वीकर होते हैं और इंट्रा जो होते हैं वो स्ट्रॉन्गर होते हैं. इसके बाद जो लास्ट है टॉपिक अबाउट द इंटरमोलिकुलर फोर्सेस इंक्लूड्स हाइड्रोजन बॉन्डिंग, दैट आई शुड कवर इन आवर नेक्स्ट क्लास. ऑलराइट.
Okay.
Okay.